Okay.
Good. The link and other facilities for the presentation seems to be okay. It's a really great pleasure for all of us to have here Professor Kara for the noticeable talk on investigations on singular minimal hypersurfaces in Lorentz space. Professor Kara, do welcome to your presentation, please.
Thank you. Before starting, I would like to thank those who contributed to the organizations of this webinar for giving us the opportunity to speak in such a beautiful organizations. Before giving the mathematical definition of singular minimal surface, let's talk about the architectural shapes of such surface. This surface appear as structures called domes. Historically, the shape of a dome has been of great interest. The construction of the domes involves a complex interplay of artistic and structural issues that require the architect to determine various variables such as the choice of materials and the desired stylistic effect. The main engineering problem to be solved is to construct a structurally sound, aesthetically appealing roof that rises over a large empty space. To achieve these, architects need the support of science. For this reason, it is of great importance to examine the domes geometrically. Thus, the first condition to be considered is that the dome is standing along its boundary by its own weights. Accordingly, inference about domes can by integrating it with a limited large homogeneous piece, a cloth whose boundary is represented by a predetermined fixed curve. The part supported by this curve turns into a static equilibrium under the force of gravity. The fabric's surface is closely related to that of the dome because a surface suspended solely by its own weight, subject to tensile forces on tangential to its interior. When the surface is inverted, it produces the optimal shape of a dome. Reversed converts the pulling force into a compression force. The inverted surface satisfies the same equilibrium equation as the original surface, so the main problem can be shaped as follows. What is the shape of a flexible hanging surface of uniform mass on which only gravity acts? Consider the one-dimensional analog of the above problem, that is when the problem is reduced to the problem of determining the optimal shape of hanging cable. The answer is the catenary with the simple expression yx for a positive constant a. The catenary has the property that its center of gravity is lower than that of any curve of equal length and with the same fixed endpoints. Catenaries have been important field of study for mathematicians and they have an important place in determining of optimal shape of arcs. For more detailed information about catenary, see these references. Some of the studies investigating the shape of surface hanging under their own weight are these. Therefore, with a row definition, the following definition can be expressed. A surface determining only by its own weight is called a singular minimal surface. Now, let's define it mathematically. Let x, y, z denote the canonical coordinates of three-dimensional Euclidean space and z vertical direction. Consider gamma a closed curve and a big zero, a fixed positive number. We construct the differential equation that parameters a surface spanning gamma with area A suspended from gamma by its own weight. Assume that M is made of a flexible, incompressible material of equal density phi per unit area. Let M be given by the graph of sigma differentiable function defined on sigma. Under the influence of weight, surfaces M reaches an equilibrium point when the weight of the center of gravity is a local extremum. Suppose the gravitational potential at a point x, y, z is the distance z to the xy plane. The head of the center of gravity is equation 1. We can suppose that A and B take the value 1, where sigma x, sigma y are partial derivations of sigma with respect to x and y respectively. Euler-Lagrange equation of equation 1 is equation 2.
2 minutes left. 2 minutes left.
Oh.
Please.
Since we are no. Since we are concerned with smooth surfaces, we only consider non-zero functions sigma in equation 2. I give the results. Basic definition. Let R1 M plus 1 be endowed with the canonical Lorentzian metric. Let phi be a smooth immersion of an oriented time like hypersurfaces. Xi unit normal vector field and H mean curvature. Let Y non-equal 0, a space-like vector non-parallel to Xi. Then Mn is called singular minimal hypersurface with respect to Y if satisfies this equation. We have problem finding cylindrical singular minimal hypersurface in Lorentz spaces. We skip. As a result, the only singular minimal cylinders in R1 M plus 1 with respect to a horizontal space-like vector Y are either the hyperplanes parallel to Y or cylinders whose generatrix is hyper-Lorentzian catenary and the Rollings orthogonal to Y. Problem 2. Finding singular minimal translation hypersurface in Lorentz space. And as a result, we find let singular minimal translation hypersurface with respect to a horizontal space-like vector Y, then it is either a hyperplane parallel to Y or a cylinder whose the generatrix is alpha-Lorentzian catenary and the Rayleigh stretch lines orthogonal to Y. And finally, consider time-like surfaces being invariant a uniparametric group of translations. In this form, we have the only singular minimal cylinders are in R1, 3 with respect to a horizontal space-like vector U, Y are either the plane parallel to Y or cylinders whose the generatrix is alpha-Lorentzian catenary and Rayleigh orthogonal to Y. Other problem, finding singular minimal affine translation surface in Lorentz spaces. An affine translation surface R1, 3 has one of the following graphs, where f and g are smooth functions, g non-equal 0. And as a result, singular minimal graph with respect to horizontal space-like vector Y of the form f this, then it is either a parallel plane to Y or a cylinder whose the generatrix is alpha-Lorentzian catenary and the Rayleigh straight lines orthogonal to Y. And these results satisfies in this form time-like surfaces, and this forms singular maximal graphs with respect to horizontal vector Y1, 0, 0. Then f equal constant and this equal. Many thanks for your attention.
Okay, we thank you, Professor Kara, for the talk. If there is any question or comment, please use the question and answer button. I will check. Are there any questions here? No. It seems there is no question or comment. So we thank again to Professor Kara.
Thank you.